Hello, this presentation is titled Robust Large Language Model Pipelines. My name is Anton Antonov. Today is September 21st, 2024. A longer title of this presentation would be Making Robust Large Language Model Computational Pipelines from Software Engineering Perspective. 5 weeks ago, I gave a version of this presentation at the Wolfram U Data Science Bootcamp, and a week ago, I gave another version of this presentation at the South Florida Data Science Study Group. So, what does this talk about? The basic premise of this presentation is that large language models are unreliable and slow. Hence, it's a very good idea to find different techniques for harnessing LLMs into a robust and effective way. So, the primary goals of this presentation is to communicate these techniques for harnessing LLMs, to expose software engineering and software architecture perspectives on LLM utilization, and to present techniques which are valid across different languages and different systems. So here this kind of is an attempt to show, to illustrate that we want AI to do the serious work, not some drawing and writing, which AI has been used a lot for. All right, so what are the pipelines? So here, let me delete the output here. This is a pipeline in which we specify how to create a certain classifier of a certain data. So we have the GS Titanic data, and we're asking to split it into training and testing parts with this ratio, 75%. Then we show certain data summary, and we can see probably here that the proportions are approximately 75%. Then we built a classifier, logistic regression. Then we show compute, show some measurements, and then we show the receive operating characteristic plots. All right, so this is a pipeline. This double long right arrow shows how the different transformations or different stages of this pipeline, how they go from one to the other. And so how we can do this with, say, LLMs. So here, it's exactly the same thing. But right now, what I'm showing here is that the different segments are actually using natural language specifications. And those natural language specifications, if I evaluate this in place, they translate to code. So evaluate in place here. So you can see it produced Mathematica code. So each of these invocations of the LLM system is producing Mathematica code, and that's plugged into this pipeline. And so here how we produce the working pipeline, which is equivalent to what we have above. And so did I evaluate this? I think I did. Let me do it again. So you can see how OpenAI is being called for each of these segments in order to translate the natural language specifications into Mathematica code. So in order to produce the same results, I use the same seed random here, and we can compare the results and the ROC plots. All right, so this here, it's explaining pipelines in another way. This is not the only way to do pipelines. And please do not get confused by the way these pipelines look. They don't need to look like this. They can be just some steps of transformations. There's some kind of linearity into the steps, and the code can be much messier. But we do have a pipeline. We have some different stages of transforming data, transforming different kind of machine learning artifacts. And after we are done with it, we do some kind of visualization, or we take this output, trained model, and we save it in some way, utilize it further. So these images here, they kind of try to illustrate the pipeline from this monadic perspective. This here, what you see is actually a monad, and this is a monad code. So the monad code, it's not that important what monadic code means, but the gist of it is that the code you have, if it is monadic, the code itself has algebraic structures, and that makes it amenable for certain operations and translations, like for example, like what I was showing here with the large language models. All right, maybe, I'm not sure, I generated these images with DALL-E. Maybe this is kind of also illustrative, or at least to some is illustrative, how the data is being processed, and what we do have a pipeline in which we do consecutive transformations of data, artifacts, and so forth. All right, so here's an outline of the talk, and again, you know, this is going to correspond to this mind map. So we're going to look into domain-specific language for large language models, prompt engineering, and example-based techniques. These are standard in a sense, and these are timeless. They're always going to apply. You apply them right now if you're using LLMs. So they always going to be in place. They're always going to be valid, so to speak. The question answering system and the grammar LLM combinations. These are two techniques which are favorite of mine. I would rather discuss them, but there should be some kind of groundwork before that. And the sixth technique is testing the data types and shapes from LLMs over multiple LLM results. This is kind of no-brainer, but it's also a technique which is, I don't see applied much, so it has to be discussed. In the other presentations, I also wanted to discuss modeling how LLMs are used and how we accumulate frustration and money while using them. But that's a very heavy topic, and I'm not going to discuss it much here. All right, so what we're not going to talk about, and what we're not going to discuss. So we're not discussing training of large language models from scratch. Also, we're not discussing the use of retrieval augmented generation, or RAG, and I'm not going to discuss, say, limitations of LLMs, like the bigger picture limitations, like why we want robustness and etc. Right now, obviously, if you have robust pipelines with LLMs, the next question is where and in what condition, you know, under what conditions they can be applied, to whom, and so forth. So we're not discussing that either. All right, so the proposed techniques, they have this transfer know-how ability, meaning other systems and other programming languages can utilize those techniques. Again, do not get distracted by the pipelines the way they're shown. I have used a specific notation and specific representation in order to have concise and didactic exposition. The large language model domain-specific language which I'm showing, it's developed by Wolfram Research. It's timeless, as I mentioned, and if we go here, let me see, yeah. So I basically re-implemented in Python and Raku the domain-specific language for dealing with LLMs described in this article by Stephen Wolfram. And so here we're going to see the variety of examples, but in order to save time, I'm not going to evaluate all of the large language model commands. So we're going to reuse some of the results. So when I have some contracted slide, this means that it's not that important. So in the previous versions of this presentation, I think only in one of them, I wanted to describe pipelines to the audience from the perspective of using different programming languages. And since I opened this slide, let's actually look at this. So imagine I have this natural language specification, use DS Titanic, group by passenger class and passenger sex, counts, right? So this is a natural language specification. The data looks like this, right? And we can see how this natural language specification has been translated to programming code in different languages, Python, R, and Wolfram language. So, all right, great. It is a pipeline because you can see how if I do this in Python or Mathematica or Wolfram language, and we first assign the data to some object, then we manipulate this object in some way and make another assignment, and then we make another assignment to find the lengths. But somebody might say, well, why you should have this object repeated? on the left hand side and the right hand side? Can we actually not do that? And yes, this is one of the solutions with R. They use this. This is the dplyr library, in which we take the data. The data is being given, to this group by default. This operator here, this is the pipeline operator, means that this argument here, this whatever thing is, this thing here is given as a first argument to this function, and then it is given to the result is given to as a first argument to this function count. So okay, well, this is a pipeline, and so there's another way to do it. So here I'm actually generating the pipelines and probably doing some examples with them. So another way to look at pipeline generation or pipeline utilization is that if you know the pipelines, you can actually generate them in some kind of streamlined manner. And again, I'm using natural language processing here. So from this specification, use the DF temperature data to construct a controller. It's not a controller, it's a quantile regression. It's when I dictated this, it was parsed incorrectly by the voice to text system. So anyway, this is a quantile regression pipeline, which we can see here has been translated into more or less correctly. If I release the hold, so this is in Mathematica, if I release the hold, we actually do get from this temperature data, we do get a pipeline, and we get some quantile regression fits and so forth, right? So yeah, this is again like this is how this pipeline looks like. What is and because I said this multi-language, so you can see it's the same perspective here. So we can do this in Python. So if I wanna apply this technique, now I can make this in Python too. It's just I'm showing it in Mathematica in order to demonstrate what is going on. Again, if I actually evaluate in place what it is, you can see this is Python code, which is going to be put under. And so yeah, this is how this is supposed to work. And there is an interesting point here. With this particular model I'm utilizing, they decided, they meaning LLMs, the LLM utilized the model, decided to put this code fences around it, right? So yeah, well, a more robust version of this, it's going to take care these code fences not to be present. Okay, the large language model failings, I would like to spend some time demonstrating the failings and why, motivate further about this presentation. So I'm going to open a notebook, which is Mathematica or Wolfram language chat book. So this is amazing actually. So we have this image here, and I'm saying, give me the names of the corresponding Ninja Turtles. And so the AI actually produced fairly good results from the masks, from the images of the faces of these artists, produced correct, as far as I know, and as I think I verified it, correct answers. Now, okay, this is great, but you see, and so this here, it's a chat book, right? And in this chat book cell, I have put this image, and I have asked, I've put some text, which is with the actual request. So the request is both the image and the text. Now, what can we do further with this though? Can we actually compute something with this? Or how I'm going to convert it, say, into a table or something else, right? So this is one of the kind of motivations, right? We're not using large language models from the perspective of this talk. We're not using them as end users. They're supposed to work, the pipelines with LLMs are supposed to work under the hood repeatedly, robustly over multiple, say, users, multiple invocations. So we're not consuming that directly in this direct manner what is being produced by the large language models. So here I'm going to use another example. So this here is a notebook with in which I have requested that I want to get some geographics plot of Cuba and the Caribbean. This is because of recent events, like recent, well, 3-4 months ago. some ships came to Cuba, and so anyway, I want to see some maps with this. We'll actually can see that we are getting more or less correct results, but they're not entirely correct, and they don't always work, and we need to kind of correct them. And here I'm showing some corrections, but I'm not going to evaluate this in Mathematica. I'm going to show it in Raku actually, because you can tell me, well, probably Mathematica is not used that much, and that's why large language models don't know about it. So let's actually have this geographics demo here with this this notebook. I'm going to do some setup here, and maybe it was I already did the setup. So here I'm creating a Google Charts persona. Google Charts is relatively old, like I think at least 10 years, maybe 12 years old library. It's a JavaScript library for producing JavaScript plots. They're pre-canned, they're very simple. So you can see here I have made some invocation here with this persona. Let's actually do it here. So now this actually, okay, first of all, you can see this is a different result from what I had previously, right? So we don't have that much of a robust, reproducible results. Although this is correct, this is a regional map of Cuba and the Caribbean, and because Cuba and Caribbean was highlighted, it wasn't highlighted as much as I wanted, right? Or in this kind of focused, zoomed way, which was previously done. And so here, we can see the generated code. This is the previous version. So let me actually show it here. As I said, the code is very pre-canned, so to speak, from Google Charts. We have some kind of more or less repeatable, more or less the same stencil code in which we just need to put data and options with different coloring and then invoke it. And basically that's it. And so this is what is happening here. And yeah, it's working just fine. Again, this is a very well-known library, Google Charts. It has a very good footprint in the web, and it's discussed in a variety of ways, say in Stack Exchange and so forth. So here, let's actually do this. I'm actually using the same persona. They already know the previous output, right? So I'm saying, okay, well, plot Cuba and Cuba's main marine port. So pretending I don't know it, that's Havana. And you can see we don't get actually a good results. And so, I mean, if I actually show the generated code, and let me actually I need to open, say, a markdown cell here. So if I put this markdown cell, well, I mean, more or less, this has been correct. It's just not visualized for whatever reasons. And yes, you can tell me you need to have a map API key. Well, no, it works also without that, right? Although some of the other elements here, which I requested, like for example, I said that I want the div ID to be port, right? It was addressed, it was given correctly. I strongly suspect something with the regions here is like if I change this, say from markers to regions, maybe something is going to happen. But we do need to have markers in order to get the plot of the actual, to have a point which is at say the Havana port. Let me actually say somewhere. None of this is particularly good, unfortunately, but yeah, this also illustrates my point fairly well. So it's just not robust enough, right? So we need to have something better than this. All right, so that's an interesting example which I'm not going to discuss. So first, let's actually look into this pipeline. So this is from the domain-specific language perspective I was talking about. We have this basic function LLM synthesize. Again, if we look at, say, this in Raku, let me see, do I have synthesize? Yeah, in Raku, this is with LLM-synthesize kebab case, and in Python we're using LLM synthesize. Let me find it here with underscore, like snake case. All right, so here I'm asking for what are the populations in India states, and okay, I'm getting some result, but for whatever reasons I also have this JSON code around it. And now, can I use this? Well, ideally I can just import the JSON code, but because of these code fences I need to kind of replace them first, remove them. Now I can also say, look, same pipeline, but interpret the result in JSON. And I think this is most likely to fail exactly for the reasons I mentioned, because the interpreter here doesn't know how to deal with the code fences. Maybe some other failings, some other inconsistencies are in the text here. I'm not going to explore this. I mean, I can see that the what this built-in JSON interpreter is having problems with is this code fences with JSON. Now, this is not necessarily LLM failing. This can be seen also as an interpreter failing. And we can ask ourselves for a variety of ways to fix this. You can see that if I change, instead of saying JSON, nothing else, actually, let's see what this nothing else is. This is one of the most useful prompts to have and to know, is to basically say, look, whatever you do, just give me the code, or just give me this form I want. Don't do anything else. Do not apologize, and so forth. Large language models, they're generative models. By definition, they cannot just shut up. They hallucinate whatever kind of stuff, and very often they produce large and redundant information, or maybe not redundant, but definitely not as concise as we might want. So here I'm saying that nothing else is, I want compact JSON without white spaces, and we get actually fairly good result. This is being parsed. This is, as far as I can tell, this is probably parsed into JSON. I think no, this is just text. And so here, let's actually do this and try to parse it. And so ideally, this actually works. We do actually get, you can see, we get this list of rules, which is more or less what we want when we can compute further. So, all right. So to mention this here, right, about large language model pipelines, what we do, this flowchart shows that typical workflows. So when we make a workflow with some parts of which with large language models, well, we obviously need to outline it, we need to design it, we make the pipeline, we evaluate it, we assess the outputs. If we have good and workable results, we ask ourselves, are they satisfactory? And if it is, we declare victory, and that's it. If they're not workable, what do we do? Do you programmatically change the outputs? Like, in the previous example, I could have, removed these code fences and so forth. So I could use my programming language knowledge or prowess to massage the results, to massage the outputs, and then do some modifications further on the outputs, not on the pipeline itself. Alternatively, I might try to do different formulation of the prompt, or I can make another application, another invocation of the large language models in order to change the prompts in some way. Like, for example, I might know how I want to change the outputs, but I don't know, or I'm too lazy to program it. I can ask the LLM if I can describe it, how to change these outputs. And if I cannot describe it, maybe I can use examples. And so this is what this example functions is. We go back to the LLM functions and we go through the whole loop again. This flowchart here can be used to build system dynamics models for modeling frustration and accumulation of money. I think this is the only time I'm going to mention this. All right. So where are we at? I basically went through the introduction here. So we're here into the main specific languages for large language models. So this, I would like to say, this kind of DSL is it's almost no-brainer. It's obvious if you want to do anything from a reproducible research perspective, not just software engineering. You basically you'll figure out that you need to separate the configuration, how you access the large language models, how you actually invoke it, what exactly is happening, and what is the post-processing. So you can see all of these elements here. This is in Python, but same in Mathematica. We saw it in Mathematica with the India functions. Let me actually go here, take this Mathematica version. So it's more or less exactly the same, right? So we have made the configuration. This is the configuration, And the actual invocation, you can see here, it's this specification. It's a list of things, right? So I have certain predefined, I have certain sentence which is being followed by a certain predefined text, which is basically a prompt. Now, this LLM prompt, it's a function. Probably wasn't clear from previously when I did it, So this is a template object or a function, but then we actually can put something here, like whatever it is, right? Like say Python, right? And then we modify this string stencil to be for a particular type of language. Obviously not just programming language, I can put whatever I want. This is what was in the previous example, right? Okay, so here, yeah, I mean, I actually had this example here, I guess, so we don't need to do it. So here we produce this a list of rules, and if I make it an association, I can actually visualize it here. So this, I mean, yeah, so you can see I'm reusing the previously evaluated results. Okay, so the inclusion of this nothing else with JSON or JSON without white spaces is crucial, because if you don't, right, if you just use the question, what are the populations of in India's states, right, we do get, let me see, yeah, we do get more or less correct results, or results which correspond to this. Actually, they don't. It's much shorter, right? But then it's not computational either. It's both short and not computational. So indicating to the LLM that we want to do something with it, or we want to use this JavaScript object notation, which kind of hints very strongly that we want data, right? It is crucial in order to produce computational results. So the domain-specific language here, these three elements here, this separation of these three phases, the configuration, configuration and the evaluator. The configuration itself is just a list of rules, like how it is shown here. It's not the actual evaluator. The evaluator is an object or a special system which goes to the large language model service, like ChatGPT or Gemini or whatever, and the actual evaluation is being obtained, and and for whatever prompt we have made here on the spot. And then the post-processing is here also reflected. We are saying that we want the post-processing to be with JSON. All right, so this unified modeling language chart or sequence diagram, it's going to show what are the stages of making making a new LLM function. So the user gives a prompt, like say what are the states, what are the populations in the states of India. Then we have a certain front-end functionality, right? This is the user interface LLM function. So this is what this is, right? So this function takes the configuration which we have, and we have another function, user interface function LLM configuration. The LLM configuration itself as a functionality, it doesn't, I mean, obviously it's connected with this LLM configuration, but it doesn't need to be that function. It can be something else. And similarly with the evaluator. So we take the configuration specification, we do some wrapping and preprocessing, we give it to the evaluator. We have an evaluator object, and this evaluator object is being used by this interface function, LLM function, to make a pure function which gives us, which is both a functions as a function, right, in the host language, be that Mathematica or Python, but also knows how to access the evaluator, right, to produce the actual result with the prompt. Ultimately, everything is just text. So the evaluator just takes some text, and gives it to the LLM service. And we get, finally, we get a handle. After we have made this anonymous function, say this, user interface function makes this anonymous function for us and gives us a handle which we can use in our computations. So if let me show you this here. If I look at the function here, this function f, this is how it looks like, right? We have these template objects and etc., right? With so we just need to put elements into in the slots of these templates. So here, if I do, so here, what are the populations in one, right? Okay, so let me actually do, maybe I should kind of do here, put some more lines. and let me do what are the populations in the top countries of European Union, right? So it doesn't need to be India or you know, like a particular kind of country or state, you know, so we can see, you know, we can get this here in this way. So this is a function. So this is exactly what is happening here. We got this handle, right? This is a pure function, and I can put some argument, and I can invoke it further. So I can invoke it in a variety of ways, right? So so here, you know, if I in populations in say in California's forests or whatever, right? Maybe we'll get something, right? Yeah. Okay. Yeah. Get something actually very interesting, right? Now, because I said California's forest, it didn't even think about people, right? It was this is an open-ended question, so we get black bears, mountain lions, and so forth. All right. This is, in a sense, I already gave these examples here. So this is just further examples, but we can have more than one argument. For example, here we have two arguments, and I'm saying what is the GDP of the gross domestic products of 1 in 2, right? So top 4 Asian countries in 2020. So actually here, let's actually look at the result. The result is markdown. So most recent models, LLM models, they produce markdown very often, both for code and as responses. And so it is crucial to have a function which interprets markdown in this kind of way. This is actually built in this Raku chatbooks, and you can see it here when I was, so this is the Python one actually. So yeah, you can see it here when I was saying that I want the different sorry, this is with the geographics. So you see when I say that I want the output to be put into HTML format, this is the reason we actually visualize it immediately. Again, this is built in Raku chatbooks, in Wolfram language, Mathematica. There should be some function which converts markdown into Mathematica cells code, right? So this is what you see here. I'm not sure can I demonstrate this here, but this is actually a very important functionality, and it's not trivial to do in Mathematica or Wolfram language Mathematica notebooks. It is kind of easy to do in Jupyter notebooks because, well, Jupyter framework is based, it's a web-based technology, or web browser-based technology, so the rendering to HTML and Markdown, it's actually relatively easy. All right, so here what I'm saying is that it's important for this kind of outputs, right? If we want to have like some kind of seamless integration, right, of the outputs with the notebook itself, we need to know how to convert Markdown into some nice visualization or rendering kind of way. All right, a couple of questions here to consider, and yeah, what other queries can we do with this, right? I mean, obviously this is very generic. Do we want to actually be that specific? Can we actually make it to have 3 arguments? So instead of GDP, maybe we can put some other argument here, another slot, and so have 3 arguments. For example, here I'm asking what are the Olympic medals of the top countries in 2022. This is this kind of function. All right, yeah, and the question is also the results we get. Can we? This is not a computational result. You see, I'm rendered this as Markdown, but how do we get a computational result? And is this computational here? And so here, for example, I mean, yeah, in some cases we might get results which are good and computational. Again, we, at least in Mathematica and Wolfram language, we need to deal with the code fences. All right, so I already went through this diagram. This is just a bigger diagram in which the actual invocation with the LLM is being shown. I'm not going to spend time to discuss it, but if you get to this notebook, you can actually see the corresponding narration here for this UML. This is a very interesting chart. This is more or less how I'm using the access to different personas, if we will, or chat cells in this Raku notebooks and in Raku chatbooks, right? So Raku Jupyter chatbooks, and the chatbooks which are also in Python. So it is using more or less the same perspective or the same design which is being shown here, and I'm going to go through this component diagram. So we have the chatbook frontend. This chatbook frontend, this diagram, it's also valid for the Wolfram language chatbooks. So we have the chatbook frontend, we have a chat cell, and we have also chat result cells. This again into these notebooks here, and we specify some input, right? Now, if there's some ID or there's some persona to be accessed, in this particular case, you can see the persona is T0 and then SB and etc. Let me actually demonstrate this. So here, this is, I have loaded this extension to, let me see, do I have it here somewhere? So this is in Python, right? And I have loaded this extension to be a Jupyter chatbook. And so here, if I clear all outputs, what is going to happen, right? So I'm okay, so I guess I haven't evaluated, I have closed this notebook and have evaluated it further. Let me actually do that. Let me load the corresponding extension. I'm going to make the corresponding access objects, right? And so here I'm saying in a chat cell, right? What is how many people live in Brazil? And I'm getting some, answer. Now this here, it's using the domain-specific language, which is being described here. Domain-specific language, not for dealing with large language model functions programmatically, but actually accessing them in cells. I'm not sure how quickly can I locate it here, but somewhere here in this article, there's some discussion how we can access. Maybe it's in a different article. How we can access in cells, how we can access process the inputs we give to the LLMs in the chatbook. And so here I'm saying that I want the previous result to be translated into Bulgarian. I'm not sure what is the audience to this presentation, but I can put different languages here. So what is happening here? I'm saying I'm using this translated prompt, and I'm getting this. I'm translating the previous result into Spanish. This caret symbol shows that. Okay. And so here, if I want to invoke a particular prompt, this is the Southern Belle speak, right? So I'm saying, hi, who are you? Well, bless your heart, darling, I'm Miss Anne, and so forth, right? So I'm similarly here, another example with a different persona, that's Yoda, and say, who are you? And again, you can see we have different IDs for the different personas or the different chat cells. And so here I can actually continue the conversation with that persona and ask, what is the color of the laser saber? They say it's a green, and so forth, right? Okay, so back to this diagram here. So I was just illustrating how we get different chat IDs. With different chat IDs, we access different personas, LLM personas. We have a database of chat objects. We can do some kind of additional prompt processing, like this translation, for example, the TERS DSL into the translation with the caret and the Spanish and so forth is happening here. We might access some prompts. We have a database of prompts which we know how to access in order to process what is happening here. And then after we have created the whole text, which is being ready to be sent to the large language model, we do that. And we can have variety of large language models, variety of configurations. This is a very useful way to deal with this kind of functionalities, to manage multiple chats. And not just from a notebook perspective, but if you have like a web service or any kind of standalone system which manages discussions with different users at different times and locations, this is one way to do it. All right, so this here we basically finished the first part. Here we're in the prompt engineering. Prompt engineering, I'll be relatively concise. And prompt engineering is lots of people, when they talk about large language models, they actually talk about prompts and prompt engineering. Using long and elaborated prompts to get robust results, Not necessarily, it's a good idea to make one, but usually with long prompts you get results much slower. They're also much more expensive, at least initially. Now the large language models, they have larger capacities for the input number of tokens, but at least, you know, like say a year ago or 6 months ago, you can very easily hit the limits of the tokens, you know, with complicated prompts. And so there's a interesting perspective which is brought up, I would say, with the Wolfram language ecosystem. They have this Wolfram prompt repository. When I was accessing nothing else and Southern Bell Speak, you know, or Yoda, you know, they're basically here. This is actually very useful to have a prompt repository, which you can, it's basically at your fingertips, so to speak, and you can very easily use it to produce new prompts. Another example here is like, let me see what is going to happen. This is some prompt I made for the Wolfram U Data Science Bootcamp, and you can see how I have utilized it here. In just a moment, it went to the other screen. So basically, in order to get the different schedules and to know what is happening, I use that particular prompt. You can see I use this when I'm asking for the different personas, and to model the personas or manage the personas, I can put different personas here. So basically, this is what is this here. It's a chat book in which that prompt which I created, you know, is being utilized in order to answer my questions about accessing through Zoom, for example, or like to accessing the talks, or to what is the schedule on a particular day and who is giving the presentations and so forth. All right, so I'm not going to discuss this this much further. The Sound and Bell Speak, I already mentioned this, and I already showed how we can do this in Jupyter and Python. So again, you know, like with prompts, I already showed this several times. It is a very good idea to have multiple prompts and to have them in some streamlined way to combine into new prompts. This is, as I mentioned, also cross-language. Let me actually move back here to the notebook here. So you can see, you know, also in Python, you know, I have this LLM prompt. If I show you how it looks like, say here. So yeah, this is a function, right? And I can say if I want to say nothing else but Python, right? So this is what is going to produce. So let me actually see, do I have this this open here? So this is the Python prompts package, and you can see in the Python prompts package, if you want to see the actual prompts, they're in JSON. So approximately 250 or 70 prompts here, they're in JSON format. They correspond more or less to the prompts in the Wolfram prompt repository. There's some additional prompts, like I think at least between 20 to 40 other prompts, which with prompts I very frequently use. I think I do not use more than say 12 prompts in my everyday practice. I think it's a very good idea to review prompts and to know certain prompts and to know how they behave, in what under what conditions they produce what kind of results. All right, so next I'm going to move to example based. This is actually a very nice way to produce robust results. And so here this is also called the so-called few shot training. And again, I was mentioning, I'm here mentioning what in the previous example with the computational results, right? Where was it? Right? They did not. We did not get actionable results. So it is a little bit of a question. How do we actually produce something more actionable in what conditions? And I want to give more elaborated examples on the Monadic pipelines. This is my opening example what pipelines are, or what I consider pipelines. So we're going to see how we can generate monadic code using examples. So this here is so-called few shot training. It's applied to massage the results. So I can use probably a prompt, like say numeric only and some other things like that. And I can probably try to convince the LLM to give me numerical results in something I can interpret. But very often when I get numerical results, they do have, say, commas, you know, for the thousands, between the thousands, right? So, but this is actually not something I can compute, at least not in Mathematica, not in Python, also in Raku. So this here is an example function in which we give on the left hand side we have a kind of output which we want to be transformed, or input we want to be transformed, and the output is on the right hand side. So we can see it here. If I create that function and if I show it, you know, it's pretty simple in a sense. Well, Gemini has a separate part of its API for giving examples, right? We give it in JSON, but in OpenAI you just construct this text blob in which is input, output, input, output, and then you can see if this input is the slot, right, which it needs to be filled in with something else, and then output is being generated. And so more or less this is what is happening here. Let me actually, I guess I did not evaluate all of the functions in the previous the previous example here, so I evaluated this, and so this is with the Olympic medals, and I'm not sure. Let's actually do the GDP3. All right, and so here I'm going to go back to the few shot training here, and I'm going to invoke this function. Right now you can see when I say that I'm basically looking for the GDP of these three countries, USA, China, Germany, in 2012. It's exactly what I was saying. It actually, the result here is not actionable. We get something more. I ask only for GDP, by the way, right? This function is only asked for GDP, but I can transform the results in such a way that they become computational. And so here now I have the GDP in the population in this form. I can remove the code fences, which I was saying earlier, and so we basically get these results here, and now this is something I can compute with. I can make this graphic, right? So, okay, great. But so what is, again, what happened here? Well, with the pipeline or the function I had in my pipeline, I'm getting some result which, although it's correct, it's exactly what I wanted, I need to process further. And this goes back to the flow chart I was showing, right? Do we actually massage this result ourselves, or do we use an LLM, which is what I'm doing here with this few shot training function? Do you use an LLM to process the results and to make them in some computational form we can use? All right, so basically this is it with this example. Now the pipeline, which is the pipeline code being produced, here I'm basically training with few short examples. I'm teaching this LLM how to produce this classification code, right? And so here, let me actually dictate. Make a classifier with nearest neighbors. So basically this produced, it's more or less what I said somewhere here, classifier creation using random forest, right? So basically this is the rule which was applied, this one here, right? But it is correct. Unfortunately, this text also has output for whatever reasons, mostly because of the way how this prompt was created, although this is valid code. And so that's why here in the actual function LLM-clcon, which I used in the example, we actually look out for this prefix and we remove it. This is what is happening here, and then we convert the text, this text here, we convert it to expression. And so here let me regenerate this pipeline, so you can see, you know, a different pipeline. And again, in every time I'm invoking this LLM-clcon, I'm going to the OpenAI service or whatever, to the LLM service, and this is being translated into Mathematica code. This is what this to-expression was doing. Now this Mathematica code, they're basically pipeline. I have this pipeline implemented already. I know how to kind of compute with those pipelines. So to some extent, this is a continuation. So after I have assigned this result to a certain object, I can produce something else. I can say, look, I want to see the receive operating characteristics with, say, with a certain size, and then we get, the receive operating characteristic with whatever size. So this is basically what was for this third part, and very powerful technique, very good way to produce robust results. This is my next topic. Again, the first three topics I discussed here: the prompt engineering, the DSL for LLMs, the example based. These are built-in mainstream functionalities of large language models. They're always going to be applicable. They're timeless. They exist in one way or the other in different programming languages, in different systems. It is another question: do you utilize them in the way, in the streamlined way discussed here, through this LLM example function? Do we have this as a function, as a user interface? But you do have access to few-shot training from the original providers of the LLMs in one way or the other. In Mathematica, Python, and Raku, this is happening in a very streamlined manner, because the DSL, the functions, basically, they generalize, they know how to use different LLMs, and this is happening through this design, how the invocation is separated from the actual access, the configuration of with the system. Okay, back to the question answering system. And so here why I'm bringing this up. So the question answering system and the grammar and LLM combinations, they also always apply, but the efforts you might put into putting them in place, the efforts you required, might over time might become a little bit too big. LLMs can be so good that you need to apply them in really some special cases. Maybe LLMs are going to be applying these techniques by default. Combining grammars with LLMs is a no-brainer. Some models they already do that. For example, Llama models, you can use a grammar to filter out the results, to kind of restrain or filter out the hallucinations of the LLMs. We're not doing that, we're doing something else. The question answering system is, I would say, it's a very powerful way to produce robust results. So instead of asking LLMs to produce large code, which happened in a sense here, right? When I was asking here with the geographics demo, we can see that we produced this full-blown HTML code, right, with JavaScript and whatnot. But ultimately, not much of this code is being changed. Especially here, when I was asking for for Havana, I mean, the input is very small, right? What is changed is just this line. Imagine that. Instead of generating all of this code, I know what my code is, right? Basically this. I just want to replace this line, given the user request. So another thing is that and the idea here is that if you request a larger code generation, that is going to be more prone to errors. But with smaller codes, just using questions and answers, right? We are less prone. We are both less prone to get mistakes in the generations, the hallucinations from the LLMs. But the other thing is that we are going to get the results faster. And private code means that it's if you don't want to share your code, right? You have some API. So the only thing the LLM would know is that there are certain parameters or combinations of parameters being combined, but they wouldn't know your code per se, right? What exactly is doing with these parameters. And the elements here, I mean, again, I basically reiterated the simplicity in which the output is much simpler than the actual, when generating a full-blown code. All right, so what is exactly happening here? Let me give some examples. So I'm using here, this is a small language model, so to speak. I'm actually using a question answering system, which is built into this in Wolfram language. It's a fine textual answer. And so here you can see that for this command, using the data df temperature, make a quantile regression pipeline for the probabilities 0.2, 0.5, 0.8 with 20 nodes. And you can see that actually that's wrong, right? Neither the 20 nodes, df temperature was put correctly, but I would have expected, right, these probabilities here to be correct and the 20 nodes to be correct. And you can see that nothing else is, I mean, yeah, basically the pipeline was produced, so the system guessed correctly that we are doing quantile regression, but it didn't guess correctly, you know, like what are the actual results. So here, this actually, it's because of the way there's some kind of, this is using LLM textual answer. So instead of using the fine textual answer which is built in, LLM textual answer is being used. And here df temperature is being correctly guessed, but also the probabilities are being correctly guessed. Again, the nodes are not being generated correctly. And I might have somewhat, let me actually see what are my settings here. Yeah, this is with the Omni model. Maybe if I change the model into something else, I might produce somewhat different results. Let me try it again, you know. And well, as this thinking, I'm going to briefly outline how this works. Oh, it's even worse. Well, anyway, this is also, yeah, okay. So basically the model I switched to, it doesn't even, it's even worse than that. And I'm going to do one more switch and I'm going to give up on this. So what is, this time this worked, and actually this worked correctly. Okay, so this is with the, I just switched to GPT-4 Omni Mini, right? Before I was using 4, in the previous I was using 4. But this here you can see, it's exactly the code I wanted to expected. The question answering system, it figures out that this is a quantile regression pipeline, and then it's bombarding this command with questions. What is the data set? What are the probabilities? What are the number of nodes? And so after those answers are being found, they're plugged into this template. I have discussed this at length in some other presentations, so I'm not going to actually discuss it much here, but I hope I have the questions themselves here. So yeah, let's this is with a different machine learning command. This is about a recommender system, and I do have the questions listed here. So here, in order to make this pipeline, I'm asking what is the data set, what is the profile. So the profile is being used to make the recommendations, how many recommendations, and should matrix factorization be applied. So the full command, make a recommender system over the data df Titanic, give the top 45 recommendations for the profile first, male, and survived. I'm asking it all these questions. What is the data set? What is the profile? How many recommendations? And you can see here that this LLM textual answer function, it has found, it's like it finds the answers to these questions, right, pretty reliably. And should matrix factorization be applied? Well, it's not discussed here. That's why you have not available. Now, these parameters, I can just plug in my stencil. So all of these elements here, they're basically slots. They're basically slots which need to be filled in. And so basically, this is how this works. This system works. It's using the answers to these questions with already predefined templates. And so here, I'm not sure should I go further with this. For example, yeah, if I add to the previous command, if I add do LSA dimension reduction, I was hoping that should matrix factorization be used to be answered, but well, it's not. And so here I'm going to make another example in which I'm actually doing classification, and this is a brand new function. You know, in the Wolfram function repository, which is being used here. So this is what is demonstrated, and you can see with same goes with classification type of workflows, right? So this is a classification workflow using the dataset DS Titanic, construct a classification pipeline for that uses nearest neighbors algorithm to classify, show the receive operating characteristic, TPI, MFCC, show summary of the data. And yeah, you can see the questions here. Which data, which classifier method should the data be summarized? They're being answered here. Now, in order this to work in a bigger system, like say to use this function concretize, you need to have a classifier. You need to have a classifier which classifies your commands into the corresponding machine learning domain specific languages, if you will, or pipelines, you know. And again, this can be done with the textual answer, find textual answer. All right, another example here. Let me see. This is, I need to evaluate the whole thing. It's Mathematica or Wolfram language. It has a style that the functions which are defined, built-in functions, but also the ones which are in the curated Wolfram language, the Wolfram function repository. The parameters, if they're given as options, they have these full names, or they're like these phrases which are concatenated in this camel case, right? Like, so we don't put, say, n elements or ns elements, right? We actually spell it out, number of seed elements. This means that if I have the certain function, like say, this is one of my favorite functions, you know, random mandala. If I ask for the options of that function, I know from these options, right? I can formulate questions, and you can see I have automatically generated for these parameters, you know, for these options of the function random mandala, I have generated these questions. And now I can make this function, which if I, let me see, this is not promising here. Let me see, it's going to work. Okay, so something is not, should a symmetric seed be used? I guess, you know, so here, what is, I'm going to reevaluate the result. Let's see, you know. Yeah, so, so I have made this statement, make a random mandala with rotational symmetry 7, connecting function is a filled curve, and the number of seed elements is 6. Use asymmetric seed, right? And so you can see the questions, right? The rotational symmetry is 7, the number of seed elements is 6, and the connecting function has been translated into something we can compute with, and then we have the symmetric seed being turned to false. All right, so basically this is it. Let me, for this example, I mean, this is basically an application of this question answering system. So the last example, actually not the last, I'm going to show this statistics of output data types. So the grammar and LLM combinations. So let's look at this motivational problem. So we assume that we have gathered lots of opinions about programming languages, and say from 200, 300, 1,000 people, every person can give opinions of several programming languages, and each interviewee, right, can gives their opinions in one sentence, right? Like several opinions, but each opinion is given in one sentence. So here this grammar which describes this kind of commands, and so here I'm going to evaluate this to get random sentences from this grammar, right? And you can see we hate Wolfram language, right? Okay, maybe let's not hate it, but yeah, so we dislike Raku, we hate vomit around Raku, we hate Python, we love Python, whatever, right? And so anyway, so here after this grammar, this is in Bacchus-Noor form. From this grammar I generate the parsers, the corresponding parsers, and I'm going to show how it is being used. Here I'm defining a large language model function, which presumably it's going to be useful when this grammar doesn't work. So what I'm saying is I have a grammar, I have a parser which can understand this kind of sentences. But imagine somebody gave a sentence which is not in this grammar cannot parse, because you can see the grammar is fairly simple. It's like it has this who, meaning I or we. There's a verb, right? Is it love, hate, and emojis, right? And then there's a language. But if they give some language which is not here, or if they use a verb which is not here, or emoji which is not here, then what we do, right? So this here is with that's why I'm making this example function with an LLM example function. You can see Python is misspelled, right? So I'm intentionally saying, well, even misspellings, they need to be treated correctly. Also, Mathematica being a synonym of all-form language, it needs to be treated in this way. And so here I'm making this this example function. So now let's actually see what we get, right? So with this function, which I just defined here, if somebody tells me we like R most of the time, again, it doesn't belong to my grammar, we do get it, you know, we do get this interpretation, we get a rule, right? Now, let's actually use the parser. The parser obviously cannot parse it, but parser can parse I love Python, right? Because, well, this is the grammar works for that. And so here I'm going to combine the two. So this function getLang opinion, if it can be parsed by the grammar, it's using the grammar, and then it wraps it in a symbol head grammar. If it cannot, it uses the large language model and wraps the result in this LLM with LLM head. So this is the so-called chain of responsibility pattern. I'm not going to go in detail, but it's very simple. Yeah, if you can deal with it, you deal with it. If you cannot, you pass it further down the line, so to speak. All right, so let's actually see some examples of this function. So here I love WL, right? This is with the grammar. I love Raku, this again with the grammar. If somebody says I love Raku a lot with 2 exclamatory marks, the grammar cannot parse it, but the LLM can. And so here we have different statements. And these statements, so you can see I'm basically sending them to this function. So some of these statements are parsed with the LLM, some of them are parsed with the grammar. And so here we can actually group the opinions. So what is the benefit of this? So when you can use the grammars, with the grammars you can get very quick, robust results and interpretations of whatever you have parsed. And so imagine that here I think it's like 50-50, you know, the grammar to LLM application. But imagine that 80% of your statements are parsed, or whatever input the users give you is parsed with grammars. You can have something much more elaborated as a grammar. And this is what usually is in the next kind of examples would be, if I wanted to elaborate on this example, is how to increase the number of verbs in this grammar, how to change the corresponding interpreter, you know, like for example, like is not here. If I want to include like, you know, I can do that there, and I need to, yeah, you can see I have like here also included. So this is in the interpreter, but like itself was not into the grammar. So let me actually include it here. And I'm going to regenerate the parsers, right? So here you can see like is being included. I'm going to regenerate the parser and reevaluate the functions here. And ideally now what I'm going to show, let's say if we have we like Perl, right? We like Perl here, LLM was used, but say Perl now, we like Perl is going to be done with the grammar, right? So this is it. So basically I can gradually elaborate, make the grammar more complicated, and then basically instead of just 50 or 60% of my user input to be parsed with the grammar, maybe 80 to 90% is parsed. Only the difficult cases are being sent to the LLMs. I mean, always someone can produce an input which is going to confuse the grammar system. Okay, so this was the example with the grammar and LLM combinations. The last example, which I was saying, statistics over output data types. So I'm going to, I mean, I was wondering, should I include it at all into this set of techniques, but it is a technique and it's not used. It's underutilized, I would say. So consider the following experiment where we're taking the discographies of, say, 100 popular music artists, say from Wikipedia or somewhere else, and then we get we have an LLM prompt that extracts the album names and the release years, and the prompt is specifying, is made in such a way that we want the results to be in JSON format. We want basically a dictionary or array of dictionaries in which we have album and year. The keys of each of the dictionaries is album and year. And so actually I'm going to demonstrate this here with Python. I fully worked out this example in Python. So let me see. Oh, I removed all of this. So here I'm defining these functions to get the actual artist names and etc. So let me actually see what artist names I'm going to get. So here, yeah, let me zoom in. So I have this artist names. I don't need a function to get a LLM function to get artist names, but well, it's one way to do it. And so here, what I'm going to do is I'm going to ask I will ask this function, this other function I defined so I have a function which gives me the discography and biography of an artist, but I have another function which is being utilized to extract the actual discographies, right, in a certain format, JSON format. Okay, so I'm going to go back to this panel here with Mathematica. So there are several questions to be answered for this setup. How often do we get dictionaries with the desired keys? If we run the extractions with the same model, do we get the same results? If we run the extraction with different models, do we get the same results? And how is this to convert the wrong formats into the format we want? And is it easy to correct the results? So let me see, do we get something here? Okay, so you can see here this looks pretty good, except it's not exactly what we wanted. I mean, I would have wanted for each of these artists, like you see, I have this kind of key album, I have some kind of string, but it is actually looking pretty good otherwise, right? So here, instead of, so let me actually go back to the result here and let me apply this. I have this technique. This technique is to apply this deduce type and actually see what are the types here. And so we can see that we have a dictionary, this associate, atom, string, right? And then vector. It's basically, we see from this signature here, that we have dictionaries which are, like, say, there's a dictionary with length 7, which is also there's another dictionary of length 1, and then this is being surrounded by some strings. And more or less this is exactly what we're seeing here in this, right? So we do have dictionaries, right? We do have these dictionaries, but then we have a dictionary with one key, and then this is here, right? Albums, and then this is surrounded by these strings. Okay, well, this is again not exactly what we wanted, but if we know it, maybe we can deal with it. We can work around it. And so basically this is what this example is showing, and there's some variety of ways to kind of see the record types. So I can see the record types for each of this, how it looks like, and etc. Now, testing this multiple times, this is actually pretty robust. So in a sense, we get the same result, but are we going to get the same result with a different model, right? And then again, how computational is this? So if I know that I'm always going to be getting this kind of output, I would know how to remove some of these elements, and I would know how to, because the whole point for each artist is to use this inner data structure here, right, with this association here, right? So, all right. So I think this was basically it, and thank you for your attention.